Okay, let's look at a few exercises. And it's important to practice thinking about how the plan generator works, because if your queries are not performing as you expect them to, then understanding how the plan generator does what it does will help you solve that problem. And maybe you're missing an index where it wasn't obvious you needed one or something like that. So for the next few exercises, let's look at these three tables from the library, and let's assume there are no indexes on any table or any column unless specified. So even the primary index, let's assume that there's some hidden column that's the primary index, so it's not going to help with any query. So the query we want to do is just titles, natural join, inventory, natural join, checked out. So just join the three tables. And we'll make some assumptions about the size and memory. So 50,000 titles in 1,000 pages, 100,000 inventory in 100 pages, and 500 checked out in 1 page. And memory can only hold 3 pages total. So we'll be able to hold 1 page from each relation at a time. So 2 questions on this. First question is, which tables would become R, S, and T if there are no indexes at all? And then which ones would become R, S, and T if there's an index on just titles.isbn? So think about that for a minute, and you should actually work this out and pause the video and then come back and we'll discuss it. Okay, this first one with no indexes is mostly just going to be determined by the sizes of the tables. So we're going to put the largest one on the outside. So R is going to be titles, and S is going to be inventory, and T will be checked out. That way we kind of reduce the amount of thrashing by putting the table that fits in 1 page on the inside. And we'll end up with, for the titles table, where that's the outer loop, we just have to loop through every record once. So we're going to end up loading about 1,000 pages for the titles table. For inventory, it's going to be number of rows in titles times number of pages in inventory. So that's going to be about 5,050,000 times 100. And for checked out, it's just going to load that page once and keep it cached. So we end up with total about, pretty much dominated by the 5 million. For the second one, the index is going to change the optimal plan. We will want the one with the index on the inside somewhere, either in the middle or the innermost. Definitely not as R. So then the question is, between the other 2 tables without an index, which one do we use as R? And we kind of fall back to the other rule and just use table size to determine that. We'll want the bigger one to be R. So R is now going to be the biggest of the 2 that don't have an index, which will be inventory. S and T, we could make either one of them be, the choice here doesn't matter too much. So let's just say S is the one with the index. So we'll do titles. And T is checked out. And what we're going to end up with now is we will have to load every page out of R, because that's the one we're just iterating over once in the outside loop. So we'll load 100 pages for inventory. For each of those, we will do an index lookup into titles. And the index lookup, how many pages is that going to load? Well, we can't really say for sure. We have to know the branching factor. Let's just conservatively assume the branching factor is only 10. Then, log base 10 of 1,000. We're going to load about 3 pages per lookup. And we have to do that for every row in inventory. So that'll be about 300,000 pages for that. And checked out, we still only need to load once since it's only one page total. We can just cache it. If we were to swap S and T, that wouldn't really change the totals here. We're still caching checked out, so it's never going to need to be loaded more than once. And if the titles was on the inside, we'd still have to do approximately 100,000 lookups into that index, because there are 100,000 potential matches with records from the inventory table. Where it might actually make a difference is since we're starting with inventory as R, so we did inventory is R, titles is S, checked out is T. So we're starting with inventory, which means we're taking this ISBN and looking it up there, since there is an index on this ISBN. There's some information missing here, but we can assume, we know more about this library, we can assume that ISBN is a foreign key in inventory, pointing to ISBN in titles. So we know that this index lookup is always going to hit. It's always going to find something. So we could not short circuit the join condition, and then we're always going to have to go and look up something in T. That's where there might actually be a miss. There may not actually be something checked out for every row in the inventory table. So if we were to swap S and T, so we put checked out in the middle and T on the inside, then we would still have roughly the same number of lookups and pages loaded, unless, say for some book like this one here is not checked out in the checkout table. So we'd look for it in the checked out table, not find it, then we can skip loading those 3 pages, roughly 3 pages, out of the ISBN index on the titles table. So it may actually be a little more optimal to swap these two, but we can't really say that without knowing the full information. Maybe those foreign keys aren't actually there. If they were, the plan generator would look at them. It would use all the information available. If they weren't, then it might decide to do it as we've picked here, with S as titles and T as checked out. Okay, here's another one, and we're kind of going the other way now. So instead of deciding what the plan generator is going to do, this time we get to add an index in order to help the plan generator make a better plan. So which index should we add in order to improve it the most? Here's the query we're doing, and it's on the chess database, and I'll show those tables in a second to give more context. But basically we want to find all people who played as the white player on a certain date. We're going to assume that games is larger than players, and players is larger than events, both in terms of number of rows and number of pages. And this time we have existing indexes, so these are just the primary indexes on all 3 of those tables, on the primary keys. So here are the tables, or at least the columns we care about. I'm leaving off some of the columns. So that's kind of a hint. Adding an index to some of those other columns in these tables would not help at all. So we have an index on players.pid, games.gid, and events.eid. And a couple things to remember here. White player is a foreign key to PID, and EID is a foreign key to EID in the events table. So let's think about first, before I let you think about this and work on this, let's think about the existing indexes we have. You might think that events.eid and games.gid will let us quickly find any matches between these 2 tables. And it will, but only in a certain direction. Given a game, we can find the event that it took place in, but given an event, we cannot not quickly find the game or games that took place at that event, because there is no index on this EID. There is an index on this one, so we can do quick lookups in there. Similarly with players. Given a white player, we could quickly look up who the player is, but given a PID from players, we could not quickly look up which games they played in as white. So keep that in mind. So back to kind of the question, what index should we add in order to speed up this query the most? And you should actually work that out and pause the video, and then we'll talk about it. Okay, I have the query and tables here kind of rearranged to make room so we can write some stuff down. The first thing to do when trying to decide which index to add to speed things up is think about what it's going to do with the current indexes that it has. So remember, it has an index on PID, GID, and EID. And this is actually already pretty good. Some of these indexes will help. So we could start on games, and we could take a white player and quickly find the player record, or we could take a game and quickly find the event at which it took place. There are no indexes, though, that will help us take a player and search for the games they played in, or take an event and search for the games at that event. We could do it, just not with an index, so it would be slow. So what that means is we're going to start on games as the outer loop, since there are no indexes that will help with a games lookup. So games is going to be R, and then we could quickly find the player that played as white, and we could quickly find the event for that game. So players and events are going to be S and T, and not necessarily in that order. They could be swapped, and it wouldn't make too much difference. They're both going to be index lookups. So that's already pretty good. So the order is going to be games, then let's say players, then events. And both players and events are index lookups. So the only problem with this is that we have to do a linear iteration through games and load every page out of games. And games is the largest table, as I stated here. So the only way we could really do better is by using one of the smaller tables as R on the outside relation. So we'll think about an index that we could add that would allow us to use games as one of the inner relations and use one of the smaller tables as the outer relations. One thing you might try initially is to try to put an index on date. Since we're doing a date filter, an index would help there. So let's think about, if I were to add my index, I get to add one index. If I were to add it on date, then we wouldn't do this. We would change it to, we would pre-filter the events. Then we would, for every event, we would have to find the games that were played at that event. We can't go straight from events to players. There's no information linking them. So we would have to do games next, and then we could do players. This events thing, though, this is basically a pre-filter using an index. So this is not the full events table. This is, say, one or two rows from it. Then this is still the full games table, and then this is still an index lookup. So it's not really that much better. We still have that bigger problem of having to load linearly scan through the largest table, which is games. So another index that would let us use a different relation as R on the outside would help. So let's think about that. Those indexes would be, if we wanted to use players on the outside, then we would need an index on games.whitePlayer so that we could take a player and find the games in which they played as white. If we wanted to use events on the outside, then we would need an index on games.eid. So we could take an event and find the games that took place at that event. So which one of those two would be better? Well, the goal would be to put the smallest relation as R. And the smallest relation is going to be events. So we will want events as R, and then the other two could be index lookups. So putting events on the outside, we would need an index on games.eid in order to allow us to do that. Then we could do events / games / players. And this is the smallest table. We have to do a linear scan through. Then this would be an index lookup, and this would be an index lookup. And that's probably the optimal choice if we only get to pick one index. If we got to pick two indexes, then this date index would also help. Turns out we don't actually just have to guess and hope that we got the right answer and put an index in the right place. We can have MySQL tell us what plan it came up with for a query. So we just use this keyword explain. You can put that in front of any query, and then instead of executing the query, it will just go as far as compiling the plan and then just tell you what the plan is. So it gives lots of information, such as like what is the outer relation and the inner relation and so on. Tells us which index it's using. It uses the term key, so like which search key is it going to use, if any, or null if there are no indexes that will help. It'll tell us an estimate of the number of rows it would have to access for each part of the query, like for the outer, middle, and inner, and so on. So let's take a look at that and see how we did with our guess of which index would help the most. So I've got this chess indexes database, which is a copy of the chess database in terms of the rows in the tables. But I've modified the tables. I've done things like remove all foreign keys because foreign keys automatically create indexes, and I just want to start with the bare bones, like only the primary index on each table. I've added GID to the games table so that acts as the primary key. So let's just see what it's going to do by default. So there are no indexes on anything other than the primary indexes. And I've got that query from the exercise. Just select star from players join games, natural join events, where PID is white and the date is a certain date. And then I added this explain in front of it. So it won't execute the query, it'll just tell me what it would do for the plan. Let's see, it's wrapping a little bit, so let me add this \G. We'll just kind of reformat a query. So let's do that. And now it's the same information, but it'll be more readable. So this is saying this is the first step of the plan, this is the second step of the plan, this is the third step of the plan. So let's see what it did. It is starting on games, just like we thought it would, because there's no index that will help there. And it's saying the possible keys or the possible indexes are none, and the index it actually used is none. And it estimates it'll have to look at 10,000 rows in order to do this step of the query. That's just because that's about the size of the full games table. And then for the middle relation, it's going to pick players, and it's using the primary index. Because we can take, for every game, we can take the white player value and do an index lookup into players, since it's just a PID, and PID is the primary key. And its estimate of the number of rows for that is just 1. And again, that's just an estimate, but if we have an index, then we should be able to very quickly go down and find exactly the player we're looking for. Then the third step is going to be events, and it's using the primary index of events. So given a game, it can quickly take that EID and find the event using its primary key. And estimate number of rows is 1. So actually pretty good, because we're using an index on both S and T, the middle and innermost relations. But so all we could do better is to try to reduce that. Let's try, though, the basic idea of, so let's look at the query again. We could add an index to help with this date part of the filter. That's actually not part of the join. This is just, do the joins in whatever order and filter by the date at some point. So let's add an index on date. Create index. I'll just call it I, because I'm going to delete it, and I want to be able to just quickly name it. On events date. Okay, now let's see what plan it picks. So here we have, not surprisingly, it is going to start on events now instead of games, because it can use that index to pre-filter out the events just on that date. And it's telling us the possible keys are primary and I, and the key it picked is I. It's saying that the primary key is one of the possible keys. It will always say that because it has to use some index to find all of the rows in that table. It's actually going to use I, since that'll help quickly filter. And it's estimating that it will access about 2 rows, so maybe it'll find 2 events on that date. Then it has to go to games, and it does, and still has to access all of the rows in the games table. Then it can go to players, it can still use that key, and its estimate is it'll access about 1 row for each time it has to look at that index. So still about the same in terms of the estimated number of rows. So let me drop that index. Drop index I on events. And let's try the other 2 options I said would be if we can put an index on that will allow us to not have games as the outer relation. So if we put an index on games.eid or games.whitePlayer, it would let us change what it uses as the outer relation. So let's create index I on games.whitePlayer first. And I stated in my answer for this question that this one should help, but would not be as good as adding it on games.eid. So let's try them both. We need parentheses, not dot. Okay, now let's explain the plan again. Okay, and the whole point of that was that we could put players as R, and indeed it did put players as R. So now it's doing a linear iteration through all of players, and it estimates that's about 7,600 rows. That's the number of players. Then it goes to games, and we can use that I index, and it estimates about 1. Then it goes to events, and it can use the primary index. Estimate is about 1. So we did better. It was, the original plan was games, then players, then events, and it was about 10,000 for the outer relation instead of 7,000, so that's better. Let's try the other one, though. Let me drop index I on games, and we will create an index on games EID. So this will let us, for any given game, it'll let us quickly find the event that it took place at. And then let's explain the plan. Okay, now it's able to use events as R, and events is the smallest table, and its estimate is lower. And so, it was starting with players, it was about 7,000 rows. Starting with events, it estimates about 6,000 rows. Then we can use the index I just created to go to games, about 1 row, and then, as always, we can use the player index to go to players, and it's about 1 row. So we were right. We creating an index on games.eid is the best option. They're all pretty good, and it didn't make a huge difference. But if you're only adding one index for a certain query, you might as well think about it and get it right and add it in the right place. So we just saw how choosing various indexes will change the plan, and this is just giving more opportunities to the plan generator to optimize and take advantage of the right data structures. We saw that with only the default indexes, the primary indexes, the plan was games, then players, then events, and its estimate was about 10,000 rows for the outer relation. After adding an index on games.eid, the plan changed to events, then games, then players, and its estimate of the cost went down. But it is important to keep in mind this is just an estimate. This is what the plan will do, but in terms of the number of rows accessed, that's totally an estimate. So if we want to actually make sure that our indexes are doing the right thing, we can profile it. So explain will tell us the plan, but profiling will tell us how long something actually takes. And you usually do get a report of how long something takes after every query, but it's not very accurate. So we can actually profile it with, we turn profiling on to set profiling equals 1. Then we can run a bunch of queries, and then we type show profiles, and it will tell us information about how long all the queries took since we turned profiling on. And I actually did this for the command for that select query that we were playing with and changing the indexes on. I ran the query a few times and took an average. So with no extra indexes, it was taking about 16 milliseconds on average. With an index on events date, it was taking about 6 milliseconds on average. And with the query on games white player, turns out it didn't appear to really help at all. And that's most likely just due to the relatively small size of these tables. If I blew them up all by like a factor of 10, then my guess is the white player index would start to help. This is probably just kind of, it's still loading about the same number of pages, even though the index in theory should help. But the actual index that we decided would help the most did. So on games EID, it actually reduced the time quite a bit, and that's the fastest in terms of only adding one index to help with this query. It's possible that we could add multiple indexes to get it down even faster. Just to wrap up a couple of things, I mentioned that I removed all of the foreign keys before doing that experiment, and that's because MySQL automatically creates an index on any column that's a foreign key. And one of the reasons for that is because foreign keys, the whole point of a foreign key is you're probably going to use it in a join because it references another table. So you might as well have an index on it, and it will speed things up. If you want to get rid of that index, unfortunately, you just have to also get rid of the foreign key. So just keep that in mind. You're going to have more indexes than you think. It's not just the ones that you create. So finally, what to take away from all of this? The best thing you can do is pick the right indexes. You have to think about how the plan generator works, though, in order to pick those indexes. And then you can verify that you picked the right ones by looking at the plan generator and profiling it. If the plan generator is not doing what you think it should, then you have to just think about, what decisions is it going to make based on table size, based on index availability? Does an index help you go from one table to another, but not the other way? You just have to keep kind of all that stuff in mind. So it's important to know how this stuff works in order to get our queries and indexes right.